I have quite the busy board up here for you, don't I? Well, we'll take it in little bitty pieces. First, I have the illusion of a three-dimensional surface. I'm no good at drawing 3D surfaces, except for paraboloids. I can do those really well. But this is just a generic z equals f of xy. And then I'm going to pick a point on that surface, x0, y0, and whatever z value goes along with it, which I would get by plugging in x0, y0 into my function, z equals f of xy. And then I just marked that point on the outside of my surface. And then, for reasons that are my own, I do a curve. The curve, excuse me, the curve is just like taking a marker and marking along the outside of that surface, passing through my particular point that I chose. So this curve C lies flat on the surface. It's just like taking a globe or a ball or whatever, an orange, and just drawing on the outside of it. So this curve is oriented. That's important. I don't want curves that I can't orient. Now, by orienting, I mean I need a direction of increasing t. This should make you think back to the beginning of the semester when we started talking about vector valued functions. I need a direction of increasing t. So if I have a curve in 3D, I can parameterize that curve with a function that tells me my x position, my y position, and my z position with respect to t. And I'm going to let t range over the real numbers. It could be a closed bounded interval, but I don't know. So I'm just going to say t ranges over the whole real line. And then I can create a vector valued function where if I knew where the origin was, the point 0, 0, 0, the endpoint of this vector would correspond to points on my curve C. So I've taken my three-dimensional surface, I picked a point, I have a curve that is parameterizable that passes through that point. I have a clear path that indicates the direction of increasing t. And going back to vector valued functions, I can create a vector valued function so that for any particular t, the terminal point of that vector I would get out corresponds to points on this curve. And all the points on my curve live on my surface. Staying back into the past, the derivative of a vector valued function, okay, if r is a position vector, then this is velocity, but what I really want to deal with is the calculus concept. The derivative of my vector valued function is a tangent vector to the curve. Now, it's going to be really hard for me to draw the illusion of a tangent vector to a curve, but I'm going to attempt to do so. So r prime, wherever it is pointing, is going to be tangent to that curve. I told you it wasn't going to look good. All right, hold that thought. Back to my surface. My surface was determined by a function z equals f of xy. Now you'll notice up here at the top, I have rewritten that, and suddenly I have a big F. I don't want you thinking that the big F has anything to do with what you used big F's and little f's with back in Calc 1, okay? This big F is just notation to let you know I'm still talking about the same surface. I'm just using a complementary letter of the alphabet, big F. Big F is a 3-variable function. And all I've done is I've taken z equals little f of x comma y. I've rewritten that equation as little f of x comma y minus z. Well, if I subtract z from both sides of that, I get 0 on one side. And so I've just named that new expression f of x comma y minus z. I've renamed that new expression big F, and I know that that is equal to 0 because z is little f of xy. Now remember, the z and the little f are giving me the z values on the surface, not just the one point that I picked. It's giving me, for every point x comma y in the domain, the 3D point x comma y comma f of xy, or f, or x comma y comma z, that lives on the surface. So everything on this curve that I drew through my chosen point also satisfies that equation up there, because this curve lives on my surface. So I've just described the entire surface with a 2D function, turn that 2D function into a 3D function that happens to be equal to 0 with that relationship between z and little f. And at the same time, I drew one curve on that surface through a point that I chose at random. I parameterized that curve. That curve has a direction of increasing t. And when I take the derivative of the vector valued function I get from that parameterization, I get a tangent vector to the curve. Now I wish I'd brought a ball, but I didn't bring a ball. But I do see something I can draw on. Some really old coffee creamer. Okay. So here comes my curve on my 3D surface. Let's see if this shows up good. All right, so there's my curve. I'll make it thick. All right, and then parameterize that curve. Pick a point on that curve. Actually, I picked the point first in my demonstration up here. Here is a point, oops. Here is a point on the curve. Parameterize that curve, find the derivative of that parameterization, and what I have is a tangent vector to the curve at that point. Well, if I'm tangent to the curve, then I'm also tangent to the surface. So this vector valued function that I magically pulled out of a hat, by picking a point, drawing a curve, parameterizing it, finding the vector valued function from the parameterization, finding the derivative to get a tangent vector to the curve. The curve lives on the surface, so if I'm tangent to the curve, I'm tangent to the surface. At the same time, back to my busy board, the total derivative of a function, z equals f of x comma y. We defined that before. We actually kind of sort of almost derived it, although I pretty much waved my hands through that derivation. The total derivative is given by dz equals the derivative of little f with respect to x, with a dx differential thrown on the end to represent changes, incremental changes in x, plus the partial of little f with respect to y, and then that differential dy on the end of that to again represent those incremental changes in y so that I could talk about taking derivatives in any direction. That's the total derivative. Now I can also take that equation for the total derivative and flip it around. If dz equals partial with respect to x dx plus partial with respect to y dy, then that means I can shove that dz over to one side, the other side, and say partial with respect to x dx plus partial with respect to y dy minus dz equals 0. Partial with respect to x of my original function that determined the curve, dx, plus partial with respect to y of my original function that determined my curve, dy, minus dz equals 0. I'm going to turn this into a scalar product. Partial of f with respect to x, comma, partial of f with respect to y, comma, minus 1 dotted with dx, dy, dz. That's the left-hand side, rewritten as a dot product. You can double check me. Dot those two vectors. You get that rewritten version of the total derivative. Somewhere down here at the bottom of my board, I see a vector of differentials, dx, comma, dy, comma, dz. Where do I see that? I see it down here whenever I look at the derivative of my vector valued function, which represented the curve that I drew on my surface. The derivative of that vector valued function gave me a tangent vector to the curve and therefore to my surface. Now I could have left this as df dt, dg dt, dh dt, but remember the part that I erased. F was how I determined my x's. Yes, I know there are two little f's up here on the board, and I just realized that this little f is not the same as that little f. Should have chosen different letters of the alphabet. Paula made a huge mistake. But I'm about to make this other little f go away, so please forgive me. This is just the derivative of x with respect to t. I could have written it as dx dt. Well, my original surface is not determined by a fourth parameter t. I just use that as a device to get me an orientation for the curve that I drew on my surface. This is just the derivative of x, the change in x, period. How much does x change when I do a tiny little increment? Oh, an increment, a differential. This is how much x changed. dg dt, fortunately there are no other little g's up here on the board. dg dt is how much y changed to get me my tangent vector. It's an incremental change in y. Oh, a differential. Differentials approximate increments. dy is an approximation of delta y. They're almost interchangeable. when delta y's and delta x's and delta z's are very, very tiny. They are approximations. Differentials are approximations of increments. dH/dt, okay, that was my change in z. Change in z, an incremental change in z. Just like with the total derivative, I can write that as dz. Oh my gosh, hey, forgiving me, please, for the inappropriate double use of the letter little f. Sorry. What I have right here, I also see when I took my total derivative, which I rewrote so that everything was on one side and 0 was on the right, as a scalar product with everything on one side and 0 on the right. A vector of differentials was one of those vectors that was being dot producted, which is not a verb. This is r prime of t. It is a tangent vector. It's a tangent vector to my curve that I drew that lives on my surface, therefore a tangent vector to my curve. And then this thing here, I'm going to rewrite this in a shorthand form. There's going to be a dot in front of that r prime. I want to go back up here to where I said, oh, let's just rewrite little z equals the original little f of xy as little f of xy minus z. Well, that's equal to 0 because that's just taking that equation and moving the z to one side, and I have nothing left but 0 on the left-hand side, and then switching those around. Call that new expression little f of xy minus z, big F of x comma y comma z. Now, imagine I asked you to find the partial of big F with respect to x. This is big F. It's little f of x comma y minus z. When you take the derivative with respect to x, you hold everybody else constant. The only place x appears is in little f. So when I take the derivative of big F with respect to x, I'm going to get the partial of little f with respect to x minus 0 because z doesn't have anything to do with x. When I take the partial of big F with respect to y, I'm going to get the partial of little f with respect to y minus 0 because z doesn't have anything to do with y. And then when I take the partial of big F with respect to z, hey, there is no z in little f, my original little f. So its whole derivative with respect to z is 0, but the derivative of minus z is minus 1. The first component is identical to finding the partial of my new big F, which seemed to have no purpose other than to get me a 0 somewhere. Actually, that was its only purpose, was to get me a 0 somewhere where I really wanted it. It's the partial of big F with respect to x. Second component is the partial of big F with respect to y. Now, don't forget, big F is nothing but taking my original equation that defined my surface and rewriting it so that instead of z equals little f, I had little f minus z equals 0. Oh, and then the derivative of big F with respect to z, little f doesn't have a z in it, so its derivative is 0 with respect to z, but the derivative of minus z is minus 1, so that little piece down here on the end, that minus 1 factor, minus 1 component is the partial of that big F with respect to Z. And that scalar product is still equal to 0. Oh, look what I have here. A vector created by some partial derivatives of a function. And that function is a function of x and y and z. And this vector I have here is the derivative with respect to x, comma, the derivative with respect to y, comma, derivative with respect to z, comma, well, no comma, derivative with respect to z, close the vector. This is the gradient vector of big F. And I dot it with that tangent vector to my surface, and I get 0. It's a lot to take in. But there's a beautiful, wonderful ending to this. The big F was a notational device. My surface was defined by z equals little f of xy, some surface. Eventually, I found a vector that was tangent to my surface. Big F is an equation for the same surface, just rewritten with a convenient equals 0 going on there. That's it. It was just a matter of convenience. This r prime is tangent to my surface. And now I have two vectors whose dot product is 0. Two vectors whose dot product is 0 when neither of those vectors is the 0 vector or orthogonal to each other. Two vectors whose dot product is 0. Two non-zero vectors whose dot product is 0 are orthogonal to each other. So what have I learned? The gradient of this big F is orthogonal to my tangent vector, to the curve that I just mysteriously threw on this graph. But that tangent vector is tangent to my surface, which means my gradient of this big F is orthogonal to the surface, except for we don't use that word orthogonal when we're talking about vectors mixed with other things. The gradient of big F is normal to the surface. Z equals f of x comma y. Now, if you don't like that representation, give me a second. This big F really is just a notational device to hold some places to make me magically get a 0 where I wanted a 0, so all my dot producty thingies worked out the way I wanted them to. That gradient of big F is nothing but the partial of my original little f with respect to x, partial of my original little f with respect to y, comma minus 1. That vector is normal to my surface. So if I need to write an equation for a line that is normal to my surface, that hits my surface at a 90-degree angle, to write an equation for a line, I need a parallel vector. I have a parallel vector. That one, because it's normal to the surface. To write an equation for a plane in 3 dimensions, I need a point. Ooh, I started by picking a point. And an orthogonal vector to the plane, a normal vector to the plane. Hey, guess what? This is normal to the surface. It is orthogonal to a tangent vector, which means it's orthogonal to the tangent plane, which means I can use that gradient or the vector from little f sub x, little f sub y, comma minus 1. And I can write an equation for a tangent plane. Pretty awesome, huh? This is a lot to digest. I understand that. All right, we're going to work with some problems.